Hello everyone. So before jumping into the next module, I would like to record a video which gives you the reason, the insight of why we learn tensor algebra and basically answers this question right over here. Why do we need tensor algebra? And because I know that most of you have this, question mark in your mind of all of these, tensorial or algebraic kind of notation and operation we learned throughout this module, how we're gonna use them or why do we learn these kind of things. So I would like to remind you once more that here in continuum mechanics, we're talking about tensors. And as you know, as I already mentioned in previous videos, tensors are different from matrices. We only use the matrix to represent the elements of a tensor. So tensors basically have two directions. For example, the a stress tensor, where it is denoted by sigma or maybe t. So it has two indices. So one is the direction and the other one is the plane, the normal to the plane that it acts on. So for example, if you remember from your mechanical materials course, if you have here the x, y, and this is the z coordinate system here. So you know that sigma xx, so the first one is the normal to this plane over here, and the second index actually shows the direction of the applied stress. Or for example, if you have this here, so this one is sigma xy, so the first one denotes the direction, the normal of the plane that it is act on, so it is this plane here, and the second subscript or index is basically the direction of the stress. So that's why we say that tensors are different from matrices, but we use, for example, this kind of notation here, sigma ij is equal to, right here, sigma xx, sigma xy, sigma xz, and then we have yx, yy, yz, zx, zy, and then we have sigma zz. So we use matrices to show the different elements of the tensor. So if you remember for example, the principal stresses, so you already remember the Mohr circle, where you found the maximum and the minimum of a stress, and it was like a circle where you had the maximum and minimum normal stress as well as the maximum shear stress. So here you can find the principal stresses from here, from the uh, this matrix here, or this tensor, it's better to say. So basically, principal stresses are the eigenvalues. So these are equivalent to the eigenvalues of the stress tensor here. And the plane that they act on are basically the eigenvectors. So simply by knowing how to calculate the eigenvalues and eigenvectors, you will be able to find the principal stresses. And then you will find the maximum and minimum stress, as well as the maximum tangential stress. Or if you recall, for example, von Mises stress, which is failure criterion for the isotropic material. So basically, this sigma, for example, von Mises, it's the square root of 3 divided by 2 sigma sigma ij here. If you know what is tensorial notation, then you will be able to calculate this sigma von Mises here. Or in the next module, which is the video, which starts right after this video, we have, we will discuss the concept of a strain and how and the mathematical formulation of strain. So you have the, for example, the material derivative here. So this concept says that if you take the derivative of some concept, so let's say that if you have a black, black parameter right over here, which could be a tensor, whether a zeros scale tensor or a vector, which is a first order tensor, or second and blah blah blah. So if you take the derivative of this tensor parameter with respect to time, you get the partial derivative of that parameter with respect to time plus velocity dot the gradient operator of that parameter. So here we use the dot product as well as the gradient concepts here. So you have to be able to calculate these. Or for example, we have the concept of infinitesimal strains or rotation tensor, where you have the dual vector of let's say the displacement gradient times something. So I'm not going to discuss this, but remember that, just in case, you have the cross product of TA and dx, where this TA is basically the dual vector of the del u, or the displacement gradient. So to get this dual vector, if you remember, so it was the anti-symmetric part. So you have del u transpose divided by 2, if you recall. So then you will be able to write this as a vector, and the cross product will give you the infinitesimal rotation tensor here. Or we have another concept, dilatation, which is the change in volume of an element. So we show it by a small e. So it is the divergence of u. So it is del dot u. So if you have u, you will be able to calculate the divergence using the tensorial operation that you've learned in previous videos and in this module. We also have the the conservation of laws, or the principal laws here. So it is rho divergence of v plus d rho dt is equal to 0. So you need to be able to calculate this dv, this divergence of v, and also this rho here is a scalar, scalar value. So you have to know how to take the derivative of this scalar with respect to time. Next, we have some other concepts like polar decomposition theorem, where you have this f equal to ru, and for example u squared is equal to f transpose f. So this is the deformation gradient, And so you should know what is the transpose of of a tensor, and you will be able to get u to, or for example, v is nothing but r u r transpose, and for example this ru here is f, so it is fr transpose, for example. And here, if you recall, we had r sorry, where we found this, for example, here. So we times it R transpose. So we have FR transpose is equal to RUR transpose, for example. And from here, we got V. So you have to know how to manipulate and how to work with these. Or for example, when you say F is equal to, so if U squared is equal to F transpose F, and F is equal to RU, so RU transpose RU, it basically is equal to U transpose R transpose RU. And you know that this is nothing but I, for example. And then you have U transpose U, and due to the the spatial properties of this U, you will get finally U squared. Next, we have for example, the Cauchy stress tensor. So the Cauchy stress tensor is Ti is equal to Tij and J. This is a tensor, this is a vector. Finally, you get a vector. So you have to know how to use this kind of notation. And for example, we have the equation of motion. Equation of motion, where for example we have the partial derivative of Tij with respect to xj ei plus rho bi ei is equal to rho ai ei. Or for example, in the tensorial format, we have this is nothing but divergence. So you should know how to calculate the divergence of a second order tensor and what it gives you, plus rho b. So here you get, so you know that the divergence will actually decrease the order of what you have, what you put into it. So if you have a second order tensor, it will give you a first order tensor or a vector. That's why you get a vector, plus this is also a scalar field, rho, it's the density, and you have these body forces here, which is bi. So finally it gives you a vector. So you have a vector plus a vector. Finally, she gives you another vector, which is rho a, and a here is basically the acceleration. So you have here another vector. So as a last example, we have for example, a stress power here. So this stress power is the trace of this, the product of T and D, where this T is the true stress, and this D is basically the symmetric part of the velocity gradient. So you should know what is the trace and how to calculate the trace to get this scalar value here, and also know that this is a power, so it is a scalar value. So these are all these are not all, but some part of the next topics and upcoming modules, where you need to know the tensor analysis, the tensor algebra, and that's why we had this module at the beginning of this course, as well as at the beginning of the book, just to get familiar with all these concepts. So you need them, and you have to use them, and you have to master in them to keep on with the upcoming modules.